Hello, Trig students. I can only imagine just how privileged you're feeling right now to be the first to take part in Mr. Allen's flipped classroom here. So good luck to you folks. Remember, just remember that you now don't have to do too many problems outside of the classroom. You just have to listen to my video, and then you don't get all of my goofy stories in class. So um, we won't have to do those goofy stories during notes now. So anyway, we're gonna enter into lesson 13.1 today. We're going away from some of the right triangle and oblique triangle trigonometry that we led off with. We're going to go into another way to measure angles, and that is with radians. So I'm going to go through my notes here, try and introduce you to that topic, and at the end I'm also going to give you some supplemental stuff that you can review on the internet as well, and even and on YouTube. So anyway, let's get going. Radian measure is just going to be another way to measure angles. It's not going to necessarily be in degrees. So first thing we need to understand is some geometry, like we did in our last chapter. And we want to talk about circles. And if you remember, if you can go ahead and read through this and you think you can fill in the blanks, go ahead and do so. Circle is a set of points, if you remember. Oop, that current layer is turned off. Look at that. Alright, set of points. We're going to go with red today. Isn't that lovely? Set of points in a plane that are the same distance from a given point. If you recall, the point that we're talking about on that circle is the center of that circle. Okay, so a circle is made up of a center and then a bunch of points that are equidistant, or the same distance away from that particular center. Okay, and a radian, a measure in radians, feeds off of this idea of a circle. So this is a unit for measuring angles. Oop, we'll get our deal to load here. All right. If a circle of radius r is centered at the vertex of angle theta, okay, so we're going to talk about this as being theta here, then the radian measure of theta is going to be defined by this. It is going to be a ratio, which, remember, a ratio is set up in fraction form. It's going to be the ratio of the arc length, okay? And this arc length we will define as S. So that is an arc length S. And it is the ratio of that arc length as it compares to the radius, which we will call R. Okay? So the number of radians that an angle is simply a ratio of the arc length, this arc length right here, as it compares to the radius. So it will be that theta in terms of radians will be S over R. Not too complicated. Now, arc length is going to be positive when theta is positive. So if we measure that angle in a positive nature, or in a counterclockwise direction, then that arc length is going to be considered to be positive as well. And vice versa. If we were to measure that in a negative fashion, or clockwise, it would be considered negative. All right. So differentiating between degrees and radians, we're going to talk about this angle theta, When no label is given with that number, we are going to assume that that is being measured in radians and no longer in degrees. All right, that's just a little something you need to be aware of in regards to radians. Now, we're going to talk about how many radians it takes to make a complete revolution. We all know that 360 degrees is a complete revolution. 180 would be half of a revolution, around there. If theta is a complete revolution in terms of radians, then that s, remember that's going to be the full distance around there, is going to be 2 pi r, and that might ring a bell. Remember that in geometry you learned that actually before you took formal geometry. Remember that 2 pi r is the circumference of a circle, or the distance around a circle. Okay, so if we've got that, theta is a complete revolution and it is equal to 2 times pi times r, it is the distance around here. Okay. So 2 pi radians here is going to be equal to 360 degrees. Okay. Those are equivalent amounts. 360 degrees is equal to 2 pi radians. Therefore, if I were to divide both of those by 2, or get half of a complete revolution, it would be pi radians, or 180 degrees. And those are important because those are going to be the conversions we use to go back and forth between radians and degrees. Okay, as we go forward here, that will kind of clear itself up. So our conversions will go like this. We at some point in time will want to go from radians to degrees, and we might want to go from degrees to radians. So we need to know what to do in the event we want to do that. Okay. So since 180 degrees equals pi radians, then we're going to figure all this off of a degree conversion. So if 1 degrees is going to be equal to pi over 180 degrees radians. And that is about, if you're talking about a decimal, it's about 0.0175 radians. So if you're thinking about, a degree measure to a radian measure, 1 degree is worth about 0.0175 radians. Okay. Now looking the other way, 1 radian is equal to, we take that conversion, 180 over pi, that is about 57.3 degrees. Okay. So here's what you're going to want to do. You will recognize here that I simply multiplied, I'm going to multiply by these conversions. If I want to go from degrees to radians, I'm going to multiply the amount of degrees times pi over 180, because, if you will notice, the label or the degrees will simplify, right? And you'll be left with radians up here. Vice versa down here, we have pi 180 degrees over pi radians. The radians would simplify and you would be left with degrees. Okay? So those will be our conversions. When we go from degrees to radians, you will want to multiply by pi over 180. When we go from radians to degrees, you will multiply by 180 over pi. Because this is simply equal to 1, right? 180 degrees is pi radians. So I'm not changing any values, I'm simply rewriting them. All right, formulas for this arc length up here, if you remember. This arc length, whoops, right up here. Going to establish a formula for that in addition to the area of this sector. So if you look at this, we drew a circle. 360 degrees or 2 pi radians. We've got a sector that has been defined by this value for theta right here. We're going to want to know how we can find the measure of that arc and how we can find the measure of the area of this particular sector. And those formulas go like this. That arc is equal to the radius times the measure in radians. Now note, this is not a degree measure. This is a measure in radians of that angle. The area will be equal to 1/2 times r squared theta. Okay? And you'll note that this area has the same components here of the arc length. So if the arc length was r times theta, we've got an r and a theta here, and then we just simply have another r and a 1/2. So this, depending on what components you have, area can also be defined as 1/2 times r times s, because this s right here can substitute in for one of these r's in this theta. So we would just have r times s. Okay? Alright, so you may want to hit pause, grab a drink, do whatever it is you want to do, and we're going to go into some of the examples here to give you an idea of how to put all of this knowledge here to work. Okay? A lot of times the ideas that we went through there on page 1 are more complicated to folks than the actual problems that we will work using this stuff. So anyway, follow along closely, and I'll have you pause and maybe work on some of these once we do an example or two. So here we want to express these in radians. You'll notice we have 75 degrees. So we're going to start with, oops, forgot to turn that layer on again. And I'll get the hang of this eventually. So we're going to have 75 degrees, and we are going to multiply by that conversion that we went through on page 1. And if you remember, the conversion we know is 180 degrees in pi radians. But the way that I try to get people to remember is, if we want to go from degrees to radians, we want to get rid of degrees. Therefore, if we want to get rid of something, of a label, we would want it in the denominator of the ratio. So we know that 180 degrees is going to go down there, and pi radians is up here. And then it is a simple conversion. Okay, 75 over 180 simplifies. You can do that typing it into your calculator or do it paper and pencil. But it will simplify to 5. Now, we want to leave pi as simply pi. And it would be 5 pi over 12 is what that would simplify to. And that is no longer in degrees. That is now in radians. Okay? So all we did was take 75 and divide by 180. It simplifies to 5 over 12. Do not round pi to 3.14. We want to leave it exact, so we will simply leave pi in our calculation. So if you want to right now, maybe pause and go do B on your own. I'll give you a second to do that. Alright, so hopefully you were able to do that on your own. I will write it out here just to see if you got it right. Again, we're going to take it pi times the conversion of pi radians over 180 degrees, and negative 225 over 180 simplifies to negative 5 pi over 4, I believe. Yes. All right. So, don't feel goofy. I'm going to ask you some questions here as we go along, and don't be afraid to answer out loud. We're going to express these in degrees. So, what is going to be different? These are in radians right now. So, I want to go from radians to degrees. So, what do I want to get rid of? What label do I want to get rid of? Well, I want to get rid of the radians. So, when I write out this calculation, 7 pi over 6 radians. The radians, remember, your label is in the numerator up there. When I multiply that by the conversion, I'm going to want pi now to be on the bottom because my radians will then simplify. So I have 180 degrees on top. And when I multiply all this out, you can do it paper and pencil, or you can plug it into a calculator, but I should know that pi radians goes away, right? And if I were simplifying, that 6 would turn to 1 and turn that 180 into 30 degrees. So I've got 30 degrees times 7, which I should know is 210 degrees. Okay, why don't you guys go ahead and try part B on your own. Maybe hit pause and ready to go. Okay, hopefully you're back now after unpausing. And you should know that I'd have negative 3 pi over 2. And to convert that into degrees, I want to get rid of pi. So I've got pi radians down here and 180 degrees. Now I'm not going to get too hung up on you writing down radians up here and writing down radians here and then simplifying. My hope is that you understand that those labels are in fact there, and I am converting to degrees, so we know that they go away. We know that those 2 would turn that into 90, and I should end up with negative, we don't want to forget that guy right out there, negative 270 degrees. All right. Okay, so there were some exact values where I was able to simplify down. There are going to be things that might not necessarily be as exact as this and go into an exact degree or into a somewhat nice little fraction here. There could be times when they want us to express this 48 degrees in radians, but I don't want it in terms of pi. I don't want an exact amount. I want it to the nearest hundredth of a radian. Therefore, I want a decimal answer. Everything goes the same way. I have to start out with 48 degrees. I'm wanting to get rid of what label? You can answer to yourself. Don't feel silly. I want to get rid of degrees, so that means my degrees needs to go on bottom, and remember it is times pi on top. So when I am rounding, we're not necessarily equal to, but we will simply take 48 degrees times pi over 180 degrees. Now when you put this into your calculator, there is a pi button on your TI Inspire. If you recall, it's down near the alphabet to the left of the H. So you can use that and you will get more precise answers than simply rounding to 3.14. And if we're to the nearest hundredth, recall that that is how many places after the decimal point? Hopefully we're in Trig. We should be aware of that. And it should be 0.84 radians. Notice that pi is no longer in my answer because I have estimated, or I'm sorry, used pi in my calculation and then rounded. Okay, so I use pi already. It is no longer in my final answer. Okay, so why don't you guys try to go the opposite direction and go from 2.3 radians and express that into degrees to the nearest tenth of a degree, and I'll give you a second to do that. Go ahead and hit pause. Alright, we're back, and we've got 2.3 radians. Again, that is not 2.3 pi radians. It's 2.3. The pi has already been calculated within that. Some people get confused on that. That's a common mistake. So we want to get rid of the radians. This is where you might want to have that radian label there when that pi is not there to remind you. So we want to get rid of radians. That means pi radians is going to be down here. That will get rid of that radian label. And 180 degrees on top. So if you take 2.3 times 180 and divide it by pi, whoops, I made the mistake right there, didn't I? I put equal to. Is approximately equal to 131.8 degrees, I believe. Now, make sure that on your calculator, remember the TI Inspires will give you an exact value by giving you a fraction. Remember that you can turn a fraction into a decimal by simply hitting Control Enter instead of Enter. You'll note above the Enter key there is an approximately equal to symbol, similar to this. Alright, let's move on to the final page of our notes today, and we will talk about finding the length of an arc and the area of the sector that is defined by that theta we're going to talk about. So, alright, a central angle of a circle of a radius 2 centimeters measures 1.3 radians. So, I need to label the information that I have. Let's switch colors. Why not? We'll go to green. I need to think about, wow, that perfect. 3 for 3. I forgot to turn my new layer on. So the radius is 2 centimeters. I like to write everything down, so I've got it in front of me what I actually know. And then remember, theta we're going to use for radians. So that angle theta is equal to 1.3 radians. Okay, radians. Okay, so moving on, we're going to find the length of the intercepted arc. So when we think about that, whoops, that was not a good circle at all. I could use my shapes, I suppose. Go down here and grab a circle. Oh, look at that. That's much better. Although let's make it blue. Okay. Okay, so when I'm thinking about this, I'm thinking that, okay, I want to find the length of the intercepted arc. I should know that I'm looking for some arc length right there, right? Okay, so, excuse me. I know that that formula is the arc length being equal to r times theta. Well, I happen to have those, so this is a pretty easy example. The arc length is going to be simply 2 times 1.3. Okay? So that arc length is simply equal to 2.6 centimeters. Alright? That's a pretty straightforward example right there. Now, for B, I want to find the area of the related sector. So now, when I think about that, again, we think about a circle again. Whoops. Put it down here a little bit more. So now, and I don't know how long this sector was, but you know, we're thinking about that. Now when we think about the area of that related sector, remember that I'm talking about this in here, right? Okay. And there were two formulas to find the area of a sector, and they just depend on what information you have. Remember that they are area equals 1/2 r squared times theta. Well, I've got both of those, so that one should be relatively easy. But I'm going to show you the other one too. Obviously, we should get the same answer, right? Because the area of the sector didn't change, just the amount inputted. So 1/2 r times s. Remember, those are the same, result in the same answer. It just depends on what you've been given. So with this, area would equal 1/2. I've been given r, so that would be 2. Don't forget to square that. So it would be 4 times the 1.3 radians. Okay. Over here, we would have area is equal to 1/2 times r, which would just be 2 times s, which I computed over here actually, is 2.6. So you can kind of see where that came from. I have a 1/2 times 2 in both of them, right? And then I had another 2 times 1.3. Well, that's what I used over here to find the arc length. So it makes sense that these two are equivalent. Okay. And either way, the area of this particular sector, and I don't know that this is exactly where it's at. It might be down here and be this whole area. We're not to that point yet. We'll talk about that later. The area of this is 2.6 centimeters. But remember, that looks odd because this is the same thing, and that was the arc length. Remember that we're talking about area here, so that is 2.6 centimeters squared. Okay? Now, we'll do a little activity in class when you come back, and then you will also be assigned the following. Lesson 13.1, page 610. We will do the multiples of 3 for 3 through 60 in that section, starting on page 610. So I hope this went okay and you understood this. This is a fairly good lesson to start out with our flipped classroom because it's not overly complicated. Now remember, you can start on this assignment if you want to. If not, you may or may not be able to get it all done in class next time, given the activity we're going to do as well. That's up to you how you want to treat that. Hopefully this didn't take too long to go through the lesson. Let me do something as well. If you want some clarification on these radians, and I would strongly encourage you to do this. I've got Khan Academy pulled up, www.khanacademy.org. That's KHAN academy.org. And I would strongly recommend you go here and start get an account or whatever. It doesn't cost anything. It's all free. Once you do that, to be quite honest with you, I don't know if you can view the lessons without doing an account or not. You'll have to just see. But if you have access to this, I would recommend doing this. If not, I believe that all of these Khan Academy lessons are also on YouTube. That's how they come up here anyway. So what I usually go to is the Learn tab right here, and Math, obviously, and oh, looky there, Trigonometry. So that's great that we've got that. And it'll go through some basic trig lessons here. I always go into that search right there, and I'm going to type in Radian. And you'll notice that here is a topic. So you can click on any of these exercises or videos individually, or you can simply go to the topic, and would be an introduction to radians here. And as you can tell right here, it's a YouTube video about 11 minutes long, and they're pretty good maybe to listen to. After you've taken my notes, it might do you good to go and just maybe listen to this, pay attention, maybe not maybe supplement your notes from this. It seems to help people sometimes. So anyway, that's my first venture at flipping my classroom. So congratulations to you. Maybe you'll be famous one day for being my students. Aren't you privileged? See ya.